Hi, I'm Austin Hester. So this will be my midterm project demo. I can't seem to figure out how to remove myself from the bottom right, like put myself at the top right. But yeah, and I can't see my mouse. See, I don't need a mouse. All right, so our intro, we got sensors and RC cars. It should be fun. So we'll go over why, what, and how the sensors considered, controllers, software, and security. So why it'll be fun and to build something and learn something, and also to learn more about like autonomous vehicles and what we could possibly do to make them better. So what? So build a self-correcting RC car. It's not quite like self-driving, but like maybe put sensors on it that, like if it's about to turn into a wall, apply the brakes. Type, yeah. Let's see so how. So yeah. So pretty much what I said. We'll just implement like proximity sensors and kind of put the pi in between the transmitter and the receiver, so it can tell it to hit the brakes or steer out of the way. So part one is sensors. So we'll go over the various sensors. We'll look at so there's quite a few sensors to consider. The tilt switch is like an angle. Knock switch, so it's like a spring loaded switch where if the spring gets knocked, it creates a signal. Reed switch is, I believe that's for like magnetic fields. I don't know how useful that would be, but ultrasonic, those are used in like parking assistance, like when your car parks itself, like it'll parallel park, those usually use ultrasonic. IR is something similar. It's uses light instead of sound, similar to like lasers, but a lot of stuff is just bouncing waves back and reading those. Gyro, that like for if you're taking a turn, it could sense that. Line tracking for like staying in your lanes. Crash sensor is just a fancy button. Lasers and lidars and cameras are proving the most useful for this. So other parts, we got a Mamba XCSC, Castle motor, 3-channel receiver transmission, a Raspberry Pi, servo, Arduino or I2C device if we want to use an analog sensor. So here's just some sensors that could be useful. I won't spend too much time on this. Relay, just higher, you can control higher voltage electronics with a small input. Knock switch, this is the spring loaded. So if it gets bumped, that spring will send a signal. Reed switch, it's a magnetic field sensor. Let's try that with the magnet tray. It was working. I haven't tried this one, the ultrasonic. I don't know how good it's going to be because the IR one that came with this kit only has like a distance of like a few like inches. And this one. So both of these are bouncing waves of some sort. One's sound, this one's light. I did try shining like I have it's a purple laser. But that didn't seem to affect it. What really affected it was this. It's probably the most powerful remote I have, like for a stereo, and it just goes crazy if I point a button and anywhere near it. It just goes insane and stops being able to sense anything. Gyro, I haven't gotten any analog working yet. I've been doing the digital ones because they're easier, but this one could be really useful for like if we really got into it and wanted to know like what position the tires are in and all that. Tilt switch, I don't know how this one might be more gradual because it's got like a ball in there and it rolls around. I feel like that'd just be kind of hidden all over the place in a car. So this is another IR sensor. So it's more specified to like tracking lines, like black lines on white paper. Better versions of it could be used for like lane detection. Laser sensor is another piece to the lasers and IR and LiDAR. They're all pretty similar. The PyCam. So this one's going to be probably one of the main parts of what I'm going to build. I don't know if I'm going to be able to get a LiDAR, but we'll put a thing like a camera on there and see if we can get it to stop when it's about to hit a wall. So it provides visual input, and it's going to be very helpful. And then this I think is like $700. I don't know if I'm going to put that in, but it would be perfect for this. You just put it on top, and it provides a 360-degree like map of obstacles around you. So that's kind of it for sensors. We'll go over the controllers. So pulse width modulation. So we're sending like a digital signal, and we modulate that to tell the receiver. It tells the receiver how to control like the servo and the ESC. So, and it depends on these cycles, like what it does. I think like 20%. It's the receiver I have is running at 20 hertz, I think, and then a 1 millisecond pulse is full throttle, and then 1.5 millisecond bursts or reverse, and then 2 is steer left, and 2.5 is right, something like that. I haven't gotten that far, but that's how it kind of works. So the receiver, just standard Traxxas receiver and transmitter. Came with the kit I got. Steering servo. So this is it's like a box of gears, a lot of torque, and able to just go to whatever rotation you tell it to, up to a point. The ESC, so this regulates voltage and like polarity of power to the motor. It's controlled with pulse width modulation. So this is like the main controller, so this drives the whole thing. And then the brushless sensor motor. So a sensor brushless motor has sensors in it that can tell the ESC where the rotors are. So it can sync that magnetic field to the rotors to provide like much quicker starts. So software design, I haven't built too much of this yet, but I'm mainly playing around with the parts by themselves at this point. But we're going to use the pulse width modulation. I found RPI.GPIO has pulse width modulation. It's fairly easy to use, documented. So that's probably what I'll be using the beginning in this. Like I want to go to C++, and once I have like a prototype. So the RPI, GPIO, people who made this have libraries for Python and C++, so switching over won't be too hard. Then OpenCV for image processing. OpenCV is awesome. And then for the overview of self-correction, so this transmitter communicates to the receiver, and we put the pi in between there. So the pi can get the signals from the transmitter, and the receiver will hear them. But if the pi senses something going wrong, then we want to apply the brakes or steer another way. So that's kind of the goal of the software. So part 4, security. I went over a lot of this in my self-selected paper review. It's always going to be, the slideshow for that. Again, I don't have a mouse. Yeah, so there's some security info here. I'll include that. And then, so attack vectors for this is like the VANETs, like they're very like they're ad hoc networks, so we could have malicious actors, so avoiding that and like knowing like who is like a legitimate, like who's giving legitimate data, like who's like the malicious actor saying that there's like a giant pile up coming out, like he's telling his car to tell other cars that so that they slow down and cause an actual traffic jam. Just to avoid stuff like that. That would be nice. So another attack surface is the physical devices, like sensor interference and jamming and in-vehicle systems, which I went over in the previous lecture. So vehicular ad hoc networks. We talked about these a little bit in class. But yeah, so it's ad hoc. So these cars are talking to each other, and sometimes they'd sync up with the network when they can. But if they're like, especially truckers on the highway, they might just be talking to each other like they do with the ham radio. But instead of that, them using the ham radio, their trucks would be doing that. Maybe they still want to use the ham radio. In vehicle systems, so you got the keyless entry, the ODB2 bus, and voice control systems are kind of the more common attack surfaces for in-vehicle systems. So physical device security, so we have physical device manipulation, like wave interference, like sound interference too, and laser jammers. So laser itself is a laser jammer if it's the same frequency. So mitigations for a lot of these things. So we can make sensors redundant. So have multiple. So some like the LiDAR are more expensive sensors. So it's really putting a premium on if you want redundancy in there. Infrared cutoff filter to block infrared lights. So that's mainly for cameras and other light sensitive sensors. Just to block the other types of light that they don't need so they can focus more on what they're supposed to be sensing. Similar, like if you have transition lenses, I have the UV cutoff filters, I guess, on mine, but so transition lenses are like the sunglasses you go in to the sun and they get dark, and you can actually put those on cameras and other sensors that, so if they have like way too much light, it's not going to damage them. And for lasers and like laser sensors, you can reduce like the receiving angle like that to prevent like people shining lasers at you. But that trades off sensitivity, and you might not see that obstacle there. You can also receive like or reduce the time. So when you send out a signal, you wait a mountain of time before you just cut that signal off and declare it lost. You can reduce that time, but that will trade off the range of your obstacle sensing. That will help against people trying to insert stuff with lasers, but you can also introduce randomness. So when you're doing the 360 laser, you can just, instead of going in a circle over and over, you can just randomly shoot out in all directions, and you know what you're expecting, but they don't, so they can't synchronize with you. So future steps. So let's see. Let's do some demo. First, here I don't have a mouse is an issue. Sorry, I need to. All right. So here's the Pi. Yeah, Pi. So we'll do the IR receiver. I know that remote really messes up with that one. So the remote is considerably more powerful than the IR receiver. So let's see what I have. So get the Pi, I don't know if you can see that. Pi with the Pi cam on there, and on a breadboard I got a IR receiver here. And then this is an IR transmitter. I don't quite know if it's working. Let's look at this. IR. Yeah, I don't think my transmitter is working. I did mess with it, but well, it's just the receiver is still working. So we have the transmitter. Oh, that is working. It's just the light's not on. So normally it's, if you can see the console here, if I can make it a little bigger for you guys. So whenever it receives a signal, it'll like print something and say how many signals. But this is like the standard transmitter. When it receives a signal, it should put it over that. Yeah, this thing's crappy, I think. But I can still use the laser. Doesn't seem to do anything to it. This is a purple laser. If I had an IR laser, it would do something. But maybe I was. But so this remote is considerably more powerful than whatever these are. That's my longest range remote I could find. It worked from the longest distance, and like this is the one. So if you can see the console there, if I press a button, it just gets, it's crazy. Like, or actually no, this isn't the IR receiver. That's why this wasn't working. This is the obstacle sensor, the distance sensor, but it uses IR. Yeah, I'm putting my hand down on it and then it goes. But if I flood it, now it's gonna think like I'm pressing buttons and it's going crazy. It's gonna think there's an obstacle there if I hit it with this, like something considerably more powerful. And then in the webcam, you can actually see my IR blast. I can't see it in real life. It's a powerful one though. But yeah, it's not going to be able to sense me getting near it anymore. I mean, it still works after I'm done flooding it, but there's no chance it's going to be of any help under this amount of like interference. So that's the what was that one? Sorry. Oh, my mouse is back. Yeah, this was the IR avoidance sensor. So this one can kind of mess with by just pointing that remote at it, that powerful IR. Did not like that. So what was the next thing? Was the so I have a video server here. So I'll run it on my PC. It has NumPy, CV2, subprocess, and we're using FFmpeg to display the stream. We can log the files, but I'm literally just saving literally every pixel. And a 30-second video is like 2 gigs. I'm not doing that anymore. Try to figure out how to save this more efficiently. But it essentially just reads from a pipe. The pipe is this ffmpeg command up here. It's on my GitHub. Yeah, so that's our ffmpeg. So we'll run this. We'll actually listen for it using netcat. So we boot up ffmpeg and we wait for the stream in that Pi. This is the Pi's console. So we'll send a 640 by 480 video. All right, let's see. So you can stream the Pi here. One thing I did try, like magnets. This video is kind of laggy. But the magnet, it just kind of sticks to it. Doesn't break it or anything. Ooh. Hold on, it's not normally doing that. Oh, my computer is chugging right now. I'm not sure what I can do. It seems to be the recording is making it very slow. We'll just do it again. Yeah, so I'm using netcat to send a TCP stream. All right, so laser. Let's see what happens with the laser. It does not like laser. So if the camera, if someone were to like point a laser at your car's camera, it's gonna be not happy about that. It's not gonna be able to recognize anything. I did try on that IR sensor. I did try here. Let me stop this out of sync video. Oh man. Okay, so I killed it on both the Pi and that. All right. So I did try this. Got a red light on this headlamp. I did try this on the IR, but I guess it's just IR only. I mean, no IR here because it wasn't really doing anything. It's just red light, which was unfortunate. I tried it though. The camera really doesn't like lights in general. Like there's, but again, like mitigations for this stuff is like the photochromatic lenses and like the IR cutoff filters and UV cutoff filters and just filtering kind of lights you don't need. Okay, so future steps. So future steps: assemble prototype. I'll probably use the camera. Some sort of laser sensor I'm wanting to use. I'll have to find one because the ones I have aren't very powerful. And then write some code using the RPI, GPIO, and OpenCV. The hard part's going to be kind of the Pi. I don't know if it's power enough to get all that. processing and make its own decisions. Might have to offload it and do like a computer bring out, make more money to buy more parts. So problems I run into, the sensors are too sensitive to like interference that I have in motion that like to be like useful in a moving vehicle situation. The parts that are good are expensive, like that the LiDAR. It's a few $100s. And choosing the right libraries, I went back and forth from different GPAL libraries and like processing libraries. Still kind of undecided on all that, but we'll see which one I end up using the most. So I have some links to some related projects. This was cool. GitHub. I found it was from like years ago that someone did a similar thing using the old megahertz band. BattleBots, that was a cool show. I always liked that. I have a couple links to my GitHub for stuff I was doing here. Some references, mainly just cool links. But yeah, that should be it for this midterm demo. Hopefully I have a prototype and some better sensors now that I know which sensors I want to use. But yeah, let's see.